I like to think I'm slightly more tech savvy, but okay.
No, this is me being not knowing how to do anything. Okay. Today we're talking about, I'm talking about IP, not intellectual property. The internet, assume that's an R. Okay, the internet protocol. So let's start with the definition. So it's broken into two parts, internet and protocol. Let's start with the internet. What's the internet?
Series of tubes.
Sure, yes, that is a possible definition. Anyone else?
It's a network.
It's true, it is a network.
It's a big network.
It is a big one, yeah. So internet is composed of two parts, inter and net. Net being short for network. Yes. And inter meaning between. So a network generally is a sort of set of objects that have some sort of relation. So if you've been discrete math, you've done graphs. Graphs are also called networks. When we talk about computer networking, these relations happen to do with communication. So the computers are communicating with each other, or not. It can be, yeah. So it's the various ways computers communicate with each other. So back in the olden day, before the internet, there was something called ARPANET, which was, so you have a bunch of research universities and the military and the government, and they all had their computers, and inside of their universities, offices, whatever, the computers were connected. So maybe like Stanford, I don't know, let's go with Berkeley. Berkeley had a bunch of computers that were connected, that were connected to each other. And then, I don't know, maybe like there was a government facility here with computers connected to each other. And then, I don't know, a government facility here with computers connected to each other. So ARPANET was a way to get these networks to talk to each other. And then eventually ARPANET became the internet. And so you have these networks, and the networks are able to talk to each other. So in this example, for example, if a computer in this network wants to talk to a computer in this network, they have to go via this network. So the internet is really not just a network of computers, it's a network, that's a fly. It's a network of networks. So there are already networks existing and you connect them. So UT, for example, has a network. And when you connect a device, like you connect your laptop, it joins the network, and then it goes out via UT's routers to access the broader internet, or it stays within UT. So each of these smaller networks are called autonomous systems. And they all have numbers, so autonomous system numbers, and that's known as an ASN. And so the internet is essentially a bunch of ASNs, or autonomous systems, talking to each other. They have internally the addresses that they have contain, and then they have routes, and I'll get into the details of all that part, some of that later. So autonomous system numbers, yeah?
Could you explain what routers are?
Yeah, I'm gonna get to routing.
Okay.
Yeah, probably shouldn't jump that far ahead. But autonomous system numbers used to be 2 bytes, but that would limit you to 65,000 about autonomous systems. So then they later changed it, I think in 2007 to 4 bytes. So now there's up to 4 billion, but honestly still not that much. So the internet is a collection of networks, and for an aside, this is not the web. The web runs on top of the internet, where you exchange HTML documents via the HTTP protocol. So let's define protocol now. Protocol is essentially a set of rules, in this case for communication. So IP is there are a set of rules for communicating across the internet. And when I'm talking about a network, by the way, almost everything nowadays is a computer. So your phones are like computers. Computers are like computers. And also, like at your home, if you've ever installed, like the ISP gives you a box, that box itself is also a computer. So really, almost everything on the internet, like even the things that control what messages go where, those themselves are computers. So when it's a network of computers and a network of networks, they're all computers. Right, so let's talk a little bit about the design of IP, why the decisions were made that were made. And to do that, let's go back to ye olden times. The phone. I don't know how to draw a phone. It looks like a banana. You know what? A phone. Okay, say you wanted to call someone. Your call would go to essentially a switchboard where there was, like, in really olden times, you know, in the movies where there's people putting plugs and stuff, it'd go to them. And then you tell them who you want to call, and then they would connect your wire physically to the person's wire that you wanted to connect to, or maybe another switchboard. So, you know, you connect to this box, and then there'd be, in olden times, people, now computers, and then, you know, this might go to another box, and then this might go to the other phone, or something like that. So if you wanted to call this person, then they would have to reconnect your line to that person. Or if you want to connect to this person, then like this person would have to connect you here, and then this line would go down. So if you call someone while they pick up the phone, it says line busy or something. That's because you get one physical line that connects you to that. So when you make a call, you end up with pretty much a wire that gets, you know, switched around in places, and you get like a dedicated connection. The internet does not work like that. So the problem with this design is that you can only have one dedicated connection at a time. And it also requires like just a lot of overhead to manage all these connections. So instead, what the internet does is for IP, you have, so the way the protocol works is that you want to send bytes essentially over the network. So you break those bytes into chunks, and those chunks are called packets. And packets typically have a header and then a body. One of the reasons this design was chosen is because it makes parsing stuff very easy. So if you want to just, like, this might have like a from address and a to address. So if you want to figure out where to send this packet, you just have to look at the very beginning. This makes it easier to hardware accelerate. This also makes it really easy to code with. So if you have like a struct in C, like this entire thing can be a struct, and then this part can also be a struct, and then you just like increment the pointer to get this part, or to deal with the packet. So it works very well with existing programming languages as well. Although at the time I don't remember if C existed. But this is a very sort of useful structure because you only need to look at header information a lot of times when you're dealing with how to move these things. The other thing about IP is that it's best effort. So best effort means there's no guarantee that your packet will get there. So you want it to send it somewhere and it might just drop off. So with phones, you get a dedicated line, but with IP, there's no concept of, you know, I want to talk to you, so now let's set up a line for me to talk to you, and then I will send stuff over that line. You just send everything you want to a, you know, whatever machines you're connected to, and they will send the stuff to the machines they want to connect to, and eventually, maybe your stuff will get there, maybe it won't. There's absolutely no guarantee with IP. Okay, so with that, we can look at, so we have this protocol That up there is an IPv4 packet header. I'll get into some of those fields. So we have this protocol that allows you to communicate between groups of people or computers, really. So we have some questions or issues we might want to solve. So how do we identify devices, right? So if we're talking about phones, you have a phone number. You call someone with the phone number, then, the phone number identifies your phone. With modern phones, it's not just a phone number. There's like with your cell phone, there's actually an identifier on the phone and then an identifier on your SIM card. Together, they make a unique identifier. But we want to identify devices. Then we need a way to send packets, these blocks of messages, and also receive them. Then we also need a way to get get an identifier. So however we identify our devices, we need a way to give this identifier to the device, or have the device be aware that that's what the identifier is. Then we need a way of discovering addresses. So like if I want to send, if I want to contact google.com, how do I know the address of google.com? Or if I want to contact a computer, like in the same room as me, how do I contact that computer in the same room as me? So we need to this is our own identifiers. And then we also need to get other device identifiers. What do they do? Okay. So this is both over the internet and locally. So we'll see that there's actually two different solutions to this problem. Let's see. Okay, so another thing we need to deal with is, say we have a box that sends a message to this box, and let's say, it passes through these intermediate, because usually what happens with the internet, and one of the good things about the internet is it's a distributed network. So you don't have a direct connection to one box, you instead connect to it via other boxes. And often there are multiple ways to get there. So let's say there are multiple paths to get here. And let's figure out the best one. Yes, how to figure out the best one? That's certainly a problem. As well as if there's an issue, how do you not end up having packets just go round and round and round and round? Like basically, imagine this guy sends a packet, and then, I don't know, there's some configuration issue and the packets just never get there. And like then you think you haven't sent the packet, so you sent it again and again, and now you just have like rounds of tons of packets. How do you prevent that? And then, what?
You didn't actually answer the question.
No.
How you pick the best route.
Oh, how you pick the best route? Oh, that's also a question that we will get to. Yeah. I'm just listing goals we want for this protocol, and then I'm going to build up to a lot of the stuff. So this motivates a lot of the things I'm going to cover. Let's see. Yeah. Okay. So I said, you break your packet into chunks. So imagine, if A has a packet this big, but B is working with packets this big. So how do you deal with different packet sizes? If B can only handle tiny packets and A is sending massive packets, how do we deal with packet sizes? Right. And also, your packets are going to be passing along many other devices. So how do you deal with corruption of the data? So there's both malicious and non-malicious. And actually, the solution to this usually is to let some other thing in the protocol stack deal with it. Let's see. Oh, also, if we already have a naming system like Google.com, how do we get IP addresses? And then there's also the question of getting a name from the IP address. So, like, if you get an IP address from Google.com, then what if you give the IP address? Is there a way to get the name? I haven't covered IP address. I've been saying identifier at this time, but I'll answer that question first. Oh, yeah. So what if we have, well, I'm running a space close. So we have, public networks, things that are accessible publicly and things that are accessible privately. Can we account for that in our design? And as well as, what if we run out of IP addresses? What do we do then? And the fact is, it wasn't anticipated that this problem would happen, but then this problem happened and we had to figure out a solution. So I think I'm missing something actually. Oh, there's also, say you do a phone call and then you're browsing the web. Both of those might be going over the same machines. Maybe your phone call is more important. Like, if your web browser takes a bit longer, then, if you're calling somebody and then their voice starts cutting out, that's really annoying. So how do you prioritize packets? Because some packets might be more important than others. Though some people would argue otherwise. Well, I'm probably thinking something, but this is a good list to start with. There's also, right, so why use IP? Because, like, if you're building your system now, like, why use IP? Like, what's so great about IP? Well, the great thing about IP is we already have the internet and everybody communicates over this protocol. So you have your typical OSI layer model or TCP IP or whatever you want to use, but usually there's like some physical stuff and then some like link layer stuff. So this would be like Ethernet and stuff. And then you have a network and then, I don't know, everything else. So IP sits at the network level. And in theory, and I think there are alternative network protocols other than IP. But because everybody speaks IP, trying to get broad adoption of those is not a feasible task. So usually they're done in small areas. So if you want to talk over the internet, which is the primary like global communication system, use IP. And the great thing about IP is you can change stuff below it and you can change stuff above it in the network stack. But as long as you make it work with IP, you can then communicate with people or devices all across the world. So what I mean by, above it, you have, TCP, UDP, or you can HTTP, whatever protocol you want above, you can implement. Below it, actually, you have like Ethernet connections or Wi-Fi, or if you want to connect over Bluetooth. If you can make Bluetooth work with IP, then you could, in theory, have something connected via Bluetooth and then communicate with other devices not connected via Bluetooth. Because as long as you can get to the IP level, you can communicate. So that's why IP is great, because it's this sort of unifying protocol that's consistent across everything. Things above it and below it. Yeah.
So what is the goal of IP, I guess, that it does?
It's to create a protocol that facilitates the usage of the internet. So the internet runs on IP. Yeah.
Did the internet exist before IP, or was it like did they develop?
Well, so I'm not actually clear on the history, but I think, I don't know if it was called IP before when it was ARPANET, or whether that protocol just became IP. They had to have a protocol for that, I don't know if it was actually called IP. If you actually look at C code, there is some weird like names that I think reference ARPANET in some of the constants. So I think a lot of the stuff definitely carried over. Whether they called it IP at the time, like whether, I mean, the standards have changed over time. So you could argue that the IP today isn't even the same as IP before. But I don't know if they call it IP. But they needed a protocol for communicating between networks, and IP was that protocol. Okay, so I've mentioned addresses a few times by accident, but so we need some way to identify devices, right? This is one of the biggest things about IP that I haven't addressed yet. So every device that wants to communicate on a network, on an IP network, needs what's called an IP address. So at this point, and it's been probably 30 years, but we still use both. There are two versions of IP that are used in public, or that are used on the internet. It's okay. Let's start. IPv4 and IPv6. IPv6 obviously was made after IPv4, but it was made like 30 years ago still. Most people, I think adoption on IPv6 is still pretty slow. The reason the primary motivator for IPv6 was to fix some of the oopsies in the IPv4 design, as well as create more addresses, because probably about 10 years ago, we ran out of IPv4 addresses. There are no more. So if you want to get them, so there are these sort of registries, like there's an international cooperation, and then each region around the world has their own sets of IP addresses. So you can buy an IPv6 address from them. Yeah?
Does that mean you can look at an IP address and know what region of the world it's from?
Well, you can know who, who originally held it, and you can know who, you have to fill out registry data. So you probably know where it's from, but somebody could have sold that IP or moved that IP address from one region to another. So the original region may have changed.
Okay.
I don't think there's, Cloudflare, for example, 1.1.1.1, that was pulled from some Asia registry. But the thing about IPv4 is you can't get, so IPv6, you'll probably be able to do that. Well, the plan is forever. Do you have a question? No. So IPv4, you can't get it from a registry anymore. You have to get it off the secondhand market. Somebody else bought an IPv4 address, you have to buy it from them, because we're IPv4 addresses. So, but we still use IPv4. So, I don't know. Yep.
Do you think moving over to IPv6 is necessary, given that everyone's just implementing NAT? Are there enough fixes to the IPv4 protocol that
No.
we couldn't just use NAT to give ourselves a ton of addresses?
So I'll get to NAT hopefully. So NAT has several problems because it breaks the end-to-end connectivity of IP. So the goal of IP is when you connect one device to another, you connect directly to its, I want your IP address, and then that device talks back to your IP address. NAT that you typically see for addressing the running out of addresses problem breaks that. So there are several issues with NAT, but we need NAT as long as we're using IPv4. And then there are just some nicer features of IPv6 that IPv4 doesn't have, and I'm gonna get to some of them. So should we switch to IPv6? Definitely yes.
It just seems with the as long as it's taking, I wonder if people were just thinking oh, why migrate over to IPv6 if I could just use NAT? And if that's justified.
Well, I mean, what's justifiable for an individual company is really up to their own decision-making process. But for the health of the internet as a whole, IPv6 adoption would be best. Right now, if you want maximum compatibility, you need to have a dual stack network where you run both IPv4 and IPv6. It would be nice to just use IPv6, but there's enough sites that don't use IPv4 for people to not be able to do that. And there's some transition stuff implemented to make it easier to transition. But I mean, there is a cost to switching to IPv6, especially for large networks. And you have to balance that as an individual business and whether or not that's worth it. But for the health of an internet as a whole, IPv6 is objectively much better. Right. So there are two different types of IP addresses, and there's also two different, these are two different protocols, and there's a lot of similarities. but then there are also some key differences. And so originally there were what's called classful addresses. So this was with IPv4. When IPv4 was created, there were 5 classes of addresses: A, B, C, D, and E. Class A addresses, I think. Okay, so I should talk about the structure of an IP address first. An IPv4 address consists of 4 bytes. That are separated by dots, usually when you see them in representation. But like the computer just sees them as 4 bytes. So like something like 1.1.1.1. So each component here can range from 0 to 255 inclusive, and that specifies an IPv4 address. So you know, this is an IPv4 address, and this is an IPv4 address. But another way to think about this is the bits that represent this. So, you know, this is like 8 zeros, and this is like 8 zeros. This is like 8 zeros. This is like 8 zeros. I'm just drawing X8 to signify that there's like 8 zeros. And so there's a notation called Cider Notation, which really comes after classes, but actually I'll get to that later. But so you have what's called a network portion and a host portion of an IP address. So if you represent it as a bunch of bits, some bits are allocated to the network and some are allocated to the host. And so the network tells you what network you're on, and then the host tells you what device you are on the network. And so every device on the same network will share this network portion, but have the same host. So the way classful IP routing used to work was you had so basically you could change, if you think of it as 4 octets, for classful class A, the first byte would represent your network, and then the last 3 bytes would be the host. So when you got a class A address, you would be given some number of these, and then your everything in that class would, all the hosts, you'd have like 3 bytes to represent your host. And then class B, you had 2 bytes for hosts, and then I'm drawing zeros, but like these identify the network, and the last 2 bytes were for the host. And then for class C, it was just 1 byte for the host, and you had 3 bytes for the network. Class D, I think, was for multicast addresses. So there are some addresses where you can send like a packet to, and then they'll be like replicated to a bunch of other devices, like everything on the network, or that's broadcast. You can also send it to a particular other, like if you can create these groups, and then if you join them, like when you send a packet to this multicast address, everyone in that group gets that message. And then class E was other reserved addresses, but they quickly realized that this is too restrictive. This doesn't allow you to finely tune how big your network is and how big your host is. So what they switched later to is classless addresses. And I think, so there's a notation called Cider Notation, CIDR. I think that stands for classless interdomain routing. So the way you do this is when you want to represent a network that you're on, like say for example, I'm on this network. So you'll do something like, so this represents an address, and then this is the number of bits used to define the network. So in this case, I'm saying there's 24 bits make up the network, which means the first 24 bits are used to identify the network, and then the last 8 are used to identify the host. So you could set this to 25, and then the first 25 bits are used to identify the network, and the last 7 are used to identify the host. So that gives you more flexibility than the classful. Yeah?
Do the last 7 bits have to be 0 in the first part, or can it, what?
Or what is the value in those last set of bits used for?
Right. So those are used to represent this is an address. So it could be a 1, and then this would be the address it represents. Everything after the slash represents how the network, the size of the network. So if you have a device that's like host name that has like a host number of 3, then you could represent it like that, and then that /25 tells you the size of the network. So you can still represent anything like that. But typically when you're just talking about the network, you will have zeros at the end of the host. Yeah?
What do you mean by size of the network? What is the /25 tell us about?
Okay, so you have a bunch of devices, and then they're what's called the broadcast domain, also called a local area network. So they're connected by a switch or an access point or both, and they all share. So when they get addresses, those addresses all share the network portion. So 2. So if all these devices are on the same local area network, then they have the first 24 bits be the same. So that signifies that they're on the same network. And the last 8 bits will identify the device on that network.
So they all start with 10.0.0.3 basically?
Or they all start with 10. What's the network? The network is identified by 10.0.0 because that's the first 24 bits.
Then what is the 3 and the address
For this one?
Or sorry, I don't have my glasses, but I think it says 10.0.0.3.
Up here?
Yeah.
Yeah, so I was just going through an example of, so the address for this is 10.0.0.3, and then the /24 tells you that it's on a 24-bit, the network size is 24 bits.
Oh, okay.
Yeah.
So
this is the full address of the device. So
that's referring to a specific device, not the whole network?
Yeah.
Okay, got it.
Yeah. Usually if you want to refer to the network, you'll use the .0.
Okay.
And in fact, I think for individual devices, there are 2 addresses that you should not use in a subnet. This is called a subnet, by the way, also, because you're taking this entire address space and then splitting it into smaller pieces. It should not be a 0. So your host portion. So you have a network portion and a host portion. The host portion should not be 0 or all 1s if you represent it as bits. The 0 I think is used to represent the network. I don't actually know exactly why it's necessary to reserve that, but I think it is. And then if it's all 1s, that's actually used to broadcast. So if you send, if this sends something to an IP address of 10.0.0.255, all these devices will get it. Well, at least that's what's supposed to happen. You can block it because sometimes this is undesirable. Yeah, so this is the structure of an IPv4 address. Let's see. So when I say each device gets assigned an IP address, what I really mean to say is that each interface on the device gets assigned an IP address. So sometimes your devices might have your phone. Well, no, not your phone. Your laptop might have an Ethernet port and a Wi-Fi card. So each of those 2 cards will actually get their own IP address on the network if you connect them both at the same time, but people usually don't. So these are actually associated usually with a single network port on your computer. So you can have multiple IP addresses associated to a single device. But usually with IPv4, the case is that a single interface only has 1 address. With IPv6, that's not the case. Yeah, so let's talk about IPv6 a little bit because, so the difficult part of this talk is if I want to cover both IPv4 and IPv6, the optimal way to do it is to talk about what's similar and what's different. But then there's a lot of dependencies. Yeah, so IPv6 is totally different. IPv6 is 128 bits. So IPv4 addresses are 32 bits in size. IPv6 has 128 bits. Let's see. So you have what's essentially actually, what was it called? You have a prefix, a subnet ID, and then or an interface identifier. Okay, this is 64 bits always. And then this stuff, sometimes the terminology changes depending on exactly what type of address you're talking about. This is also 64 bits. So, okay, let's talk about how IPv4, IPv6 addresses are represented. They're represented in hexadecimal in groups of 2 bytes. So, let's see, FF, I'm pretty sure it's FF. Yeah, in groups of 2 bytes. Okay, so I'm going to explain what this means. Okay, so this identifies a network on IPv6. This is very different from IPv4. So when you're writing them out, there's like a standard way of writing them out that is a sort of shorthand, because writing out 120 bytes, even in hexadecimal, is extremely tedious. So first, you write them in hexadecimal, then you have 2 bytes, and then every 2 bytes you separate with a colon. So you can do like yeah, and then you keep colon separating until you get to the end of the address. But there's another thing. If you have a 0, like if this is a 0, you just write that as FFF. So you drop in each of these segments, any leading zeros are dropped. Then so if you have like a bunch of bytes here and then a bunch of zeros and then a 1, any groups of zeros you can collapse into a dot dot, but you can only do that once. So if you have like a group of zeros in one spot and a group of zeros in another spot, I think you can only collapse them in one spot. So you have this double colon, which indicates everything in between here and there is zeros. Does that make sense? And then you can subnet as well. So this is like the same notation. An important thing to note though, with IPv6, you cannot subnet below a 64. And when I say below 64, this number can't exceed 64. And that's because the last 64 bits are reserved by the interface identifier. So clients can actually pick this. So unlike in IPv4, where you have to go get an an address, I'll get to that. Here you can generate your own based on random number or MAC address or all sorts of things. And because it's 64 bits, the probability of collision is usually low, but then you do a check to see if anyone on the network is using that same thing, and if not, then you pick another one. But so the important thing is that with IPv6, you only have these 64 bits to pick different networks. You can't step into these. So when you're picking different networks here, typically your ISP, if they're doing it right, will give you about 56 bits as a prefix, and then you get the last 8. You get the last 8. And so you can create up to 2 to the 8 networks if an ISP gives you a gives you a 56-bit network. So the point is there's a lot of IP addresses, so much so that you can be given, you can give a small chunk of address space and create your own like internal networks. The other thing is, yeah, okay. So with both IPv6 and IPv4 in terms of addressing, there are some common things. So I'm going to talk about 3 different types of addresses. your regular public addresses. I'm not sure if they're actually called public addresses, but what I mean to say is pretty much typical addresses that public-facing hosts have. So if you want to communicate over the internet, you have to use these addresses. Then there's private addresses, and then there's site local addresses. Oh, okay. Well, I guess we'll just talk about IP addresses today. I'm not done. I'm not done. This is. Normally, I write a lot of content, and then the talk finishes in 30 minutes.
Yeah.
This time, I got sucked into talking about IP. Well, actually, I don't know if I got sucked into it. I guess there's just a lot to talk about. Okay, so let's see. Right. So there's 3 address types. When I say public address, I mean you can contact a device over the internet using that address. And there's private addresses. So these are intended for internal network use. So like UT has private addresses in use. Most of your home networks will have private addresses. You can use these addresses however you see fit inside your network, but you're not supposed to communicate over the internet with these addresses. And then site local addresses are addresses that are only supposed to be restricted to a broadcast domain. So when I say broadcast domain, like when you broadcast to like a .255 on a /24 network. So everything more clearly, everything within the same network is on a broadcast domain. Yeah.
Okay, so I'm really new to networks, but I understand that there is a MAC address that's unique to every device.
Yes.
Why do we need local IP addresses if we have that?
So site local. So when you're communicating over IP, you have to communicate using IP addresses. So
like the router sort of.
yeah.
Oh, it's not in the packet.
But if you're sending IP packets, you still need to have an address in there, and there is a use case for this that I'm going to get to. So when you get public addresses for IPv6, everyone can get their own. Every device. UT doesn't actually have it, but they just haven't been able to IPv6. For IPv4, there are not enough addresses to give every single device their own IP address. So what you typically do is you have a network with a private address, and at some point they do translation, where they, when you go from inside the network to outside the network, they swap out the IP address and they do some clever tricks in order to make things look like they're working. But really, so you can communicate with private IP addresses just fine within a network. And then site local addresses, so with IPv6, in the specification, there's a mandate that requires you have a site local address for every interface. So IPv6, there's usually multiple addresses. Usually you have a public address and a site local address on an interface. For IPv4, there's also a site local address. What happens there is if you try to get an IP address from your network and the network doesn't give you one, maybe you didn't connect to the network properly, or maybe something's broken on the network, your computer will default to a site local address. So these site local addresses are all in the same network. So all the computers that fail to get an IP address dynamically will fall back to the site local and they'll be able to talk to each other. That's the use case in IPv4. In IPv6, that's also the case. But even if you can get a public address, because IPv6 is designed to work with multiple addresses, you just also keep that address attached to your interface. And then with IPv4, if you're in UT and then at your home, your IP addresses might be the same, but because they won't go over the internet, it's fine. With IPv6, the recommendation actually is to still have, because there's so much address space, is to still have unique addresses that are designed for local use, but they're still different. So you're supposed to, the prefix part in the IPv6 area, you're supposed to randomly generate so that you don't end up with collisions with other people. Are we out of time? Okay. Well, I mean, this is a good stopping point for talking about, another thing you might hear, so for IPv4, these are called RFC 1918 addresses, because that's the RFC that talks about them, but people will just refer to those addresses as RFC 1918. So this is, yeah.
Suppose you were asked to create a spreadsheet of IPv4 subnets for a hypothetical company. Do you think you could, do that within like the 2-hour time limit?
What 2-hour time? I mean, which company?
Wait, what was the company that we did for?
You think about CCDC?
Yeah,
Well, it depends entirely on the company. I mean, it depends entirely on their network. So if you have a huge list of subnets, because like the way these subnets work is, I can have just a big chunk /24, and like this is one network. Or I could be like, well, no, I want to have I don't know, let's go with 2 to the 6 networks, so 32 networks. And instead I, go at /30, and I have, what's 2 to the 6? 16 times 4, 64. I could have 64 /30 networks, and then still use the same number of IP addresses as this. But these are fundamentally different networks. So if you create a list of networks, it depends on how they're designed. So maybe. Anyway, this is a good stopping point.
Do we have any
For
questions on Zoom?
Addresses. Oh, there was.
Oh, dang. Okay.
No questions.
All right.